Okay, so today we are going to start this topic uh, called graph coloring. So you can see some several colorings of a graph, and before we formally define this, let us look at how we come to think of such questions of coloring. So here's a typical question that you have a mobile service provider, and they usually have to purchase the right to use certain frequencies from the government, or whoever is controlling the network. And then the question is that how many different bandwidths, or how many different frequency ranges that they need to purchase with some constraint. For example, let us say that one company has already three different frequency bands available, and they want to expand into a new area. And when they try to expand to this area, they will have several mobile towers which are going to broadcast the signal, and this tower will broadcast. Let us say one tower will broadcast only in one frequency. Now, that's our simplification assumption for the time being. Now, two towers, suppose you have two towers and they are within, let us say, 20 kilometers, then we don't want them to use same frequency, because if they use same frequency, there could be interference, and there will be issues related to this. So to avoid that, we will make sure that if two towers are within 20 kilometers of each other, then they should get different frequencies. Now, so the plan is to build several towers so that all the areas are covered, but also to make sure that there is no interference. So the question is that if they come up with a plan like of layout of the towers, they can ask whether we can actually use only the three frequency available to assign the frequencies to the towers. So is it possible to do that with the current setup? And otherwise, they have to change the layout and then find a better one. So this is a typical question that we want to answer. And how do you do something about it? Right? So let us say that the company has managed to come up with the following data, that you have the tower locations and the distances between them. So let us say that you have five towers, A, B, C, D, E. And then the distances between the pairs of towers are given in this table, right? So between A and B, the distance is, let's say, 17 kilometers. A and C is 24, A and D is 25, A and E is 19, and so on, right? So you have this data that is given to you. Now, given this information, what do you do, right? So how do you define or how do you solve the previous question? So of course, since we are working with graph theory, we are going to define a graph based on this information, and this will tell you what to do with it. So in this example, one can see that there will be interference between towers only if the distance is less than 20 kilometers, right? So otherwise, you don't have to worry about it. So what we are going to do is that we are going to define a graph with the towers as the vertices, and if the distance between two towers is less than or equal to 20 kilometers, we will put a line joining them, right? So in that case, you get a graph, where the distance between there is an edge between two towers if the distance is less than. So now we have A to B is 17, so we need an edge. Then A to E, we need an edge. Let's say this is E. Right. Then B to C, there is an edge. and then C to D there is an edge, right? And any other edges? I don't see any other edges. Okay, so we have these 5 edges in this graph. And now the question is that so we want to find a frequency distribution, right? There are 3 different frequencies available, so that we can do this. Now suppose they had only 2 frequencies, then there will be trouble, right? Because suppose you are using frequency number 1, assigned to our A, then of course B and E cannot be given 1. So if you are using only 2, then they must both be given 2. There is no connection between B and E, therefore that they can be given the same frequency, right? So the distance is at least 20 plus kilometers. Now when you come to D cannot be given 2, so it can be given 1. C cannot be given 2, it can be given 1, but then D is also adjacent to C, so I cannot use 1 here. So with just 2 colors or 2 different frequencies, I won't be able to do this. So since the company has 3, then they can use the 3rd frequency at C, and they will be. So this is a typical application of what's called graph coloring. Basically, we are partitioning the vertex set to what we have earlier defined as independent sets, or you are going to give colors to the vertices such that adjacent vertices get distinct set of colors. So another example is that let's say that there is a conference that is to be conducted, and we have a list of registered participants, right? And then they have talks which are planned. Now, to reduce the duration of the conference, typically what people do is to have several parallel sessions, right? So you will have like if you have a graph theory conference, you can have talks on, let's say, coloring, then graph decompositions, another session, graph algorithms, another session. I mean, this way people arrange several sessions in parallel, hoping that there is not much interest of the people attending the algorithm session to attend the coloring. But of course, that may not be the case. So now one can ask the following question: suppose there is a participant who want to attend a pair of talks, right? So a couple of talks. Then we don't want to assign the same slot for these talks, or you don't want them to be happening at the same time. So now question is that what is with this restriction, what is the minimum number of slots that is required so that we can have this, and also like the number of slots has to be minimized so that the duration is as minimum as possible. So you have the list of participants, you have the list of talks, so you can ask them for preferences, which one you want to attend, etc. Collect this data, and then they can model. And what will be the model? Well, each talk can be a vertex, right? Because it is going to be representing some time where it is going to be happening. And then, yes, so you have a question? No. So somebody raised a hand. Yes, sir. That was by mistake, and I was going to say the participants will have complete graph on the set of um, vertices they choose to attend, like the talks that they order. Why complete? Sir, because if they want to attend 3 talks, we have to have an edge between all the 3 talks uh, so that none of them get the same calorie. So we can't have stars. Well, so depending on like for example, let's say that a participant want to attend talk 1, talk 2, and talk 3, then of course they will be forming a clique. That is true. Yes. So if one participant, yes. So of course usually like nobody want to attend all the talks, right? Usually that like I mean the interest I mean, of course, there could be one person like that. In that case, like there is no other choice. You have to conduct each one separately if you are going with this restriction. But otherwise, it may not happen. So in typical cases, that is not always the case. So you will choose what is the best of this talk that you want to attend, and then according to your interest and all. And then when you choose this one. Huh?
What for if a participant wants to attend, say, K talks, on those K vertices, the graph will be complete, has to be complete.
Ah, yes, of course. Yeah. Yeah. So, so here is the. hmm, okay. So where were we? Yeah. So the question is that like how do you frame this in terms of our graph question? So we are going to form a graph where the talks will be the vertices of the graph, right? And then there is an edge connecting two talks or two vertices if some participant want to attend both of these talks. So then you will end up in a graph with this conditions. And once you form this graph, the question can be like you want to basically find the you want to basically partition the vertex set into different uh, independent sets, right? So that the number of independent sets is minimized, right? Because when you have such a partition, each partition can be like okay, this is one slot, then each of these partition can become slots because they are independent sets. There is nobody who is going to attend all of them, and that will give you the minimum number of slots required. So basically, we are framing or modeling this question also in terms of graph coloring. So in fact, these two problems are of entirely different nature, like in some sense, and they come from different contexts, but it has the same solution, so to speak. So what we are saying is that we have we have one tool, and then we have several possible uh, questions which could be solved using the same idea. And of course, there could be many more examples when you can think about. Uh, for example, like several kind of exam scheduling can be like very similar to this. But there could be other things, like for example, you want to color the maps. So we'll talk about that later, right? You want to give adjacent districts different colors or adjacent countries different colors, and you want to minimize the number of colors that we use. So all such questions can be all solved using the idea of graph coloring. So formally, what is graph coloring? So when we say coloring, we usually mean vertex coloring, unless we have some additional terms which explains what kind of coloring we are looking at. And we usually also mean a proper coloring. So in the context that we are going to work with, we mostly talk about proper coloring, where adjacent vertices will be given distinct set of colors, or if two vertices are getting the same color, then they are not adjacent. So such a coloring is called proper coloring. Of course, there is another notion of improper coloring, where you can allow vertices which are adjacent to get same color. So you are not partitioning into independent sets, but then we can put some conditions on the type of subgraph that we get if you look at the same type of color class. For example, I can say that if I look at the vertices of a particular color class, the subgraph induced by these vertices must form a subgraph of maximum degree at most 1, maximum degree at most 2, or regular graph, like all kind of conditions you can put, or it should be edges. So all this is possible. So this is a wide variety of questions that we can ask with just the notion of partitioning, and each has its own application. So we'll come to a couple of these distinct coloring questions. But for the time being, we look at the proper coloring, which is just a partition of the vertex set into independent sets. So an example here. So you have a graph and you have two different colorings of this graph. These both are the graphs complete by Kotak graph K33, and you know that you can give several types of proper colorings. So what are the colorings? So here, like I give the same color to one to these two vertices, which is 1 and 1, right? Then 2 and 2 is given to these two vertices. These two are given the color 2. Then this vertex is given color 3, and this one is given color 4. On the other hand, in this I use a different coloring where I give these three vertices which form an independent set with color 1, and the remaining three vertices which form another independent set with color 2. So both are proper coloring because adjacent vertices does not get the same color. On the other hand, if I had given color 2 to this vertex, right? So I had given color 1 here, but instead it was color 2, then these two will be adjacent with the same color, so it's not proper. So I will not allow such colorings uh, for the time being. So we are looking at proper color. So one of the typical questions is, what is the minimum number of colors which will do the job, right? Because when we want to partition, like for example, the earlier questions were to minimize the number of partitions, right? And minimize the number of time slots that is going to be used for the scheduling, or like minimum number of colors for the map coloring, etc. So our aim is usually try to minimize. Of course, if you want to minimize, then you have to first show that there is such a minimum that is possible, right? Of course, we can try to look for like what is the lower bound, whether there's an upper bound, etc. So these questions are natural questions now. So the chromatic number of a graph is defined as the minimum number of colors such that the graph admits a proper coloring using that many colors. So the chromatic number of a graph is usually denoted by the Greek letter chi of g. So chi of g says the minimum number of colors with which we can color the vertices of the graph. So in the previous example, we had these two different colorings. So here it uses three colors, and here it uses two colors. Of course, one can ask, can you do with less number of colors, right? So, can you do with one? Of course, if there is an edge, we know that we cannot do with, with just one, because the adjacent vertices of the edge, right? They should get different colors, so we need at least two. So since we know we need at least two, and we have a coloring with just two colors, we know that that is the best possible. So therefore, we know that chromatic number of this graph is actually equal to 2. So here are several graphs, and we want to find out the chromatic numbers of it. So the first example, we see that we have the complete graph on 4 vertices K4. And what is the chromatic number of this graph, right? So you see that if you start with any vertex, and of course I can pick any vertex, the first vertex, and give it color 1 always, right? That is possible. So I give it color 1, then its neighbors, cannot get color 1. So I know that this cannot be given color 1, so it must be, let's say, 2. But now 2, 1 and 2 are both adjacent to this vertex, so I cannot give either 1 or 2 to this, so therefore this must be 3. And since the graph is complete, all these 3 are adjacent to this vertex, so this must get a differential. So we know that we need at least 4, and we have a coloring with 4 vertices, so the chromatic number is actually equal to. What about the next graph, right? So what is the chromatic number of this graph? So if you look at this, well, you can start with color 1 for some vertex, whether I give color 1 here, then this vertex can be given color 2 because it cannot be color 1. Now the question is that how do you go proceed further? So one way is to try to force the coloring that you try to do. But of course, there is another question: is that is that method that you use the best way to do it, right? Because depending on the order that you choose, we can sometimes land in trouble. But anyway, let us see how do we do it here. So in this case, let us say that I have 1 and 2, and of course this cannot be 1. So if you are using only 2 colors, this must be also 2. But my idea is to try to use just 2 colors and see if there is any problem, right? Now, because it is only 2 colors, this one must be given 1. And then I see that, of course, I cannot give 2 to this one, and 1 also I cannot give. So I cannot do with just 2 colors. So I need at least 3. So I give color 3. Now, of course, this changes the scenario, right? Once we see that we need 3 colors, maybe the first starting order may not be the best, but maybe it might work in this case. We will see. So I know that this is 2 and 3, 1, 2, 3. And now, what about this one? I can either give 1 or 2 here, right? Of course, this cannot be 2. This has to be 1 or 3. So let me give 1 here. Right? Then I can give color 3 here, and I can give color 2 here. And since I have a 3 coloring, and I could not do with less than 3, one can see that this is actually equal to 3. Then we have this graph where we have a cycle, right? And I start with color 1 here, let's say color 2, then 1, 2, 1. Of course, I cannot give 1 here. I mean, I can give 2 here. So I have a 2 coloring, and since I need at least 2, this is actually equal to 2. What about this graph? Well, I have 1, 2, 1, 2, 1, 2, and I need 3 here because I cannot give either 1 or 2. So if there is an odd cycle, you see that you need at least 3. So these are very easy. Now you come to this graph, which is the famous Peterson graph. And then you ask what is the minimum number of colors that you can. Of course, you see that there is a 5 cycle. We know that there is at least 3 colors that you are going to use. Now, if you can find a 3 coloring, then we are good, right? So we know that chromatic number is actually equal to 3. But otherwise, we have to show that 3 is not possible, and then you need to use a 4. So how do you proceed with a question like this? Of course, finding the smallest one is not always easy. It's one of the very difficult questions. It's going to be quite hard. In computer science terms, it is going to be NP complete. It's very difficult, and we will NP hard. And finding the exact value is NP hard, and asking even whether it is less than or equal to some number is NP complete. So now here is the question, like for the Peterson graph, what is the chromatic number, right? So one way to approach this is that we know that each color class must be an independent set, right? So since we know that each color class must be an independent set, one way is to pick a large independent set and then color it with one color and then see like how well you can do. Of course, it may not always give the best, but you can try. So let's say that I give color 1 to this one, right? Then of course I cannot pick the adjacent ones, so I can pick either this one maybe, right? So this is also 1, and then maybe I pick this one. Then is there any other vertex I can pick? I cannot pick this or this. Because these are adjacent to 1, I cannot pick this or this, they are adjacent to this. And so I have picked only this. Right? Maybe I can do better. Let's say that I pick uh, this and this. Oh, I have to use a different color. I pick this and this, and then I pick, let's say, this and this. These are all this form an independent set. So I give color 2. Done with this maybe. And then I have another independent set which I can give color 3. Color 3. So I have managed to do with 3, and because there is an odd cycle in the graph, I know that we need at least 3. Right? So therefore, the chromatic number of this graph is equal to 3. Okay, so we have these examples, and now what about these graphs? So I want you to work out these two examples and show the chromatic number of these two graphs are equal to what number, and show that why it is minimum, right? So you have to give an argument why it is equal to that number, right? If you say that, okay, you have come up with a coloring with 5 colors, and then therefore the chromatic number is 5, that is not a proof, right? So you have to show that for coloring is not possible to show that 5 coloring. So you have to give a coloring, and you have to show that smaller number of colors, no coloring is possible. So it's not always easy, but these examples you should be able to find an argument. Now this second example is quite interesting. So we will come to that come to that little later. So if you can actually, like, maybe not in today's class, but in another class, and then like if you can find out that argument why for the second graph, you can find a nice argument to show the chromatic number. It would be nice. So think about this. So one way to learn about graph coloring is basically to take graphs, like simple graph that you can come up with, some nice graph that you find in your textbook, any picture that you see of a graph, you try to think about, like, how do you color this graph. Okay? And it's very important that you do this. If you do it for several of this, you will get a better understanding of how this thing works, and it will help you to solve questions also. So many of them have some nice properties that you can observe and use that property to come up with some arguments. So here are some questions. For example, what is the chromatic number of complete graph on n vertices? So we know that the graph is complete, each of the vertices must get a different color because any vertex is adjacent to any other vertex. So therefore, we need at least n colors. What about if the graph is a cycle on n vertices?
No is even, 3 is odd.
What?
2 if n is even, 3 if n is odd.
Yes. So this is again like something we already saw, right? And what is the chromatic number of the complement of the the complete graph? Well, the complement of the complete graph is the empty graph. You have only only vertices and no edges. It's an independent set. So I can give the same color to all the vertices. So it is actually equal to 1. Now suppose you have suppose you have a graph G and you have a graph H which is a subgraph of G. Okay. So if H is a subgraph of G, then can you see the relation between the chromatic number of G and H is that the chromatic number of G is greater than or equal to the chromatic number of H. Right? This is immediate, because suppose chromatic number of G is some number, then you can you can give a coloring to the vertices of G, right, in which the adjacent vertices get distinct colors using that many colors. Now, of course, because H is a subgraph of G, right? The for H, this property is still true that the adjacent vertices get distinct colors, and therefore the chromatic number of H cannot be larger than the chromatic number of H. Right? So therefore, any subgraph should have a chromatic number which is upper bound by the chromatic number of the graph G. So what does this tell you? That if G has a complete graph on T which is a subgraph, then the chromatic number of G must be larger than or equal to the chromatic number of the complete graph, right? So which means that chromatic number of G must be greater than or equal to T. So this T is called the click number of the graph, right? I mean, if you find the largest such click, then of course it is a click number. So the click number of graph is the cardinality of the largest complete graph as a subgraph. So therefore we see that chromatic number of a graph is always greater than or equal to the click number of the graph. Okay. So given a graph G, we have the chromatic number is at least the click number. Now we know that the click in a graph, of course, makes the chromatic number large, right? If you have in a large click, then you have a large chromatic number. But is that the only thing which makes the chromatic number large? Can you have a graph where the click is small and the chromatic number is very large? Okay? So we already saw that if you look at odd cycle, the odd cycle has chromatic number 3, where the click size is actually only 2, right? Because there is only 2 vertices. Which I mean, there is no triangle, right? In an odd cycle of length at least 5, there is no triangle. But you see that you need 3 colors, because if you are trying to alternate, you will end up in trouble at that, right? So therefore, we need at least 3, and it is larger than the click number of the graph, right? Which is just 2. So, but now the question is that can it be even larger, right? Either there is a change of 1, that is okay, but can it be arbitrarily large? It turns out that it can be arbitrarily large. So I want you to think about some nice example where you have the you have a graph whose chromatic number is larger than, let's say, uh, let's say k plus 2, and and the click size is only let's say k, right? So difference at least 2 or difference at least 3. So can you come up with some examples of graphs where the chromatic number increases by more than 1, right, from the click number? So think of some small graph like that. Okay, so take it as a question to ponder, right? Think about it. Now,
But the the least the chromatic number can't be greater than twice the click number, though, right? Because then we'd get another play connected subgraph. Basically, the click number would change.
what?
The chromatic number, sir. The chromatic number say there is a click number k.
Okay.
Now the chromatic number can't be greater than 2k, because if it was greater than 2k, that would mean that there is another subgraph which is more than k complete. So the click number has to change.
No, why it should have a larger complete graph? I mean, that is what I don't understand. Okay, so here is another thing to think about. Show that you have graphs with no triangle, right? So if there is a click of size at least 3, there is a triangle inside it, right? Because when you have larger complete graphs, you should have several triangles. In fact, any 3 must form a triangle. Now show that there is a graph with no triangles but arbitrarily large chromatic number. Okay? This is another interesting question to think about. Okay, so what we are saying is that So you have, let us say, a function which maps, function C which maps the vertex set of G to the set 1 to up to K. Now, such a map is called a proper coloring, provided if the inverse function C inverse of J for any J is an independent set, right? For each color so the numbers are called colored. So usually when we work with graph coloring questions, if the number of colors is very few, like 1, 2, 3, 4, or 5, we will use like red, blue, green, etc. For coloring. But if the number of colors is more, we will always use the numbers 1, 2, 3, etc. for the colors. And then the question, now in turn, like the minimum is, what is the minimum case such that there is a map from the vertex set of G to the set 1 to K, such that adjacent vertices, right? So U is adjacent to V, then C of U is not equal to C of U. Okay. So now we have a function, then the inverse map, right? C inverse J, like what are the free images of J? They form an independent set for every J. Then the coloring is said to be proper color. Now the set of such colors, such set of such vertices is called the color class corresponding to that color. So if C inverse I is the set of vertices, then those vertices form the color class I. And since we are looking at proper colorings, it will always form a partition to independent sets, right? Okay, so so we know that if there is at least one edge in the graph, then the chromatic number is greater than or equal to 2. Okay? Now suppose you have a graph in which there is no odd cycle. So if there is no odd length cycle, then I claim that the chromatic number is at most 2. There are very easy proofs. There are several proofs. So one is that so you take this graph, pick a vertex, right? And we can assume that the graph is connected. Otherwise, each component you can do this, right? So pick a vertex, and then so color each vertex y in the graph with the color which is distance of x comma y modulo 2. Right? So what is distance of x y modulo 2? Basically either 0 or 1, depending on the length is even or odd. Now the distance is even, then you will give color 0, and if it is odd, then we will give color 1. So because there is no odd cycle, and we have already proved that if a graph has no odd cycle, then the graph is bipartite, and in this case we saw that any walk between a pair of vertices, right? So if you pick a vertex x, then every walk to a vertex have the same parity. So therefore, the distance will have the of course it's the minimum thing. It will have the same parity anyway, right? And it's kind of well defined in the sense that there is not going to be any different paths which will lead to contradiction, right? So therefore, we can do this, and this will work out if the the graph is basically having no odd cycle. Of course, another way to prove is that since we already proved that a graph without odd cycle is bipartite, we have a graph and we take the bipartition, right? So what is the bipartition? It is partitioning the vertex set into two independent sets. And once you have two independent sets, each independent set can be given one of these colors, right? Color 1 and color 2. So that we have a two color. So that is another way to prove this. So if the graph has no odd cycle, then we know that the chromatic number is at most 2. But now if there is an odd cycle, then we know that the chromatic number is at least 3, right? Because a graph which is not bipartite, having an odd cycle means that you need at least 3, right? So for 1, 2, 3, etc., we can immediately see, right? So just look at the graph and immediately find out whether it has chromatic number is 1, 2, or 3. But unfortunately, for k greater than or equal to 4, we don't have any such simple characterization. Okay, for graphs with chromatic number greater than or equal to k, right? So if the chromatic number is greater than or equal to k or not, we don't have any simple characterization. Of course, for specific cases we have some complicated characterizations, but we will come to that later. So now one question is like, what makes the the chromatic number of a graph large, right? So we already saw that if you have very large clique sitting inside, very large complete graph sitting inside, then the chromatic number becomes naturally large, right? So the existence of large cliques, right? So makes the chromatic number very large. So if you have a large clique, of course, the size of the clique will make the chromatic number at least as big as that. Of course, it could be much larger. So this is one parameter which, of course, makes the chromatic number large. Now, then the other parameter. Can you think of some other parameter, whose absence makes the chromatic number large? So if you have a very large independent set in the graph, of course, we know that we can give all that vertices in the large independent set with the same color, right? So if you have many large independent sets, then each of the independent sets can be given separately, one of these colors, and then you have finished with so many vertices. Then the remaining you can just see like what is the best you can do and things like that. So now if you have if you don't have very large independent sets in the graph, right? If the all the independent sets are, let's say, of size 2, right? So if a graph has independent sets of size 2, right, the largest independent set is of size 2, then we know that you cannot use one color more than 2 times, right? Because independent set size is at most 2, so you cannot use one color more than 2 times. So we need at least the number of vertices by 2, right? That many colors will be required. So therefore, absence of large independent sets will also make the chromatic number large. So this is the way to basically think about so you see that if even if you don't have large cliques, if you can somehow make sure that there is no large independent set, that will also do that. So that is how one actually come up with such graphs. So I want to see, right? So if the chromatic number of graph, of course we know that it is at least the clique number omega of g. But now we know that if the graph has independent number, alpha of g is the largest independent set, the cardinality of the largest independent set. So therefore, the number of vertices divided by the independent set, that is also a lower bound on the chromatic number, right? It cannot be smaller than this, right? Because each vertex cannot be given. I mean, so no color can be used on more than alpha of the vertices, and therefore these colors minimum should be there. So therefore now we have this inequality. Chromatic number is greater than or equal to max of the clique number and the number of vertices by the alpha, right, which is the independence number. So n by alpha and omega are two parameters, and maximum of these two will be a lower bound for the chromatic number. Now from this one can show, like I want you to think about and prove it. Why, right? That the number of vertices by the chromatic number of G complement is less than or equal to number of vertices by, right, order of graph by the alpha of G, which is less than or equal to chromatic number of G, and which is less than or equal to chromatic number of G plus 1 minus alpha of G. Okay. So these inequalities I want you to prove. And once you have shown this above things, it will actually follow from this with some observations. Okay, so this is a good question that you can think. a small digression from what we were doing, so that you can basically think about some thing related to coloring before we go further. So I want you to introduce to some operations on graphs. So there are three operations that I am going to define now. So the first one is what is called the join of graphs. So what is join of graphs? So if G and H are two graphs, then the join is the graph obtained by you taking the disjoint union of this graph. That you take the graph G, take the graph H, put them together without doing anything. That is a disjoint union. Okay? So you take the disjoint union, but now what you are going to do is that you are going to add all possible edges between G and H, right? Because if you look at G and H as just the vertex H, you can put a complete bipartite graph in between them, right? So that is what we are going to do. So we are going to make every vertex of G adjacent to every vertex of H, and every vertex of H adjacent to every vertex of G. But we don't do anything within G or H. So such a graph is called the join of two graphs. Given this, so here is some example, right? Given this graph, first one is G, and the second one is, let's say, H. So the G join H is the graph on the right side, where you have the graph G sitting as it is, graph H sitting as it is, and then every vertex of G is now made adjacent to every vertex of H. Right? These are the white edges. So you have a complete bipartite graph between the vertices of G and H. So if G and H are independent sets, you are going to get exactly that. That is a complete bipartite graph. So in this case, there is an independent set here and another single vertex which is independent set. So what is the join? It's basically the complete bipartite graph K 4 1. Right? 4 vertices here and 1 vertex here. So this is the complement of K4 and this is just K1. So you get K4 1. Another couple of examples. So you have the edge, which is K2, and its join with complete graph K3 is the graph K5. So if you take the join of two complete graphs, then you will always get a complete graph as the result. So you will get complete graph on the sum of these two vertices, the odd edge. So K2 and K3 will give you K2 plus 3, which is K5. Because all the edges, are there within K2 and within K3, and we are adding all possible edges between them, right, by doing the join. Now, on the other hand, if you take independent sets, right, so I have K2, K2, and K2 bar, right, K2 bar, K2 bar, and K2 bar. Take the join of these independent sets, like 2 times, right? So you will get a graph like this. So here I have a graph, right? K2, 2, 2, right? So we have this, adjust between this and to any other two, etc. like this, right? So we have such graph. This is K2, 2. So uh, this is called a complete multi-parted graph. It's a tripartite graph. There are 3 parted sets. Each one is an independent set. So you can have many of these. You will get, these are called, these are independent sets in the graph, right? So the independent set size is 2 here, right? You will see that. And then you will see that the chromatic number will be basically the number of, bounded by the number of vertices by the largest independent set and things like that. You can verify. So take such examples and work with this. I think before defining, so we have already finished the time for today. So I will define the other products and all in the next class. So we will wind up today with this and see you in the next class, unless you have any questions.